Yes, this is the story of an engine, a famous one, the 18-liter, 1100 cubic inch Ford GAA V8 tank engine. This was a modern marvel at the time it was produced in the 1940s, and it continues to stand the test of time when it comes to gathering the attention and starry-eyed view of gearheads who not only love history, but who truly appreciate mechanical simplicity and effective engineering. This was an ultimately successful engine built off the failure of another. It was born in circumstances that can only be described as clouded with intrigue, and its creation is yet another example of its manufacturer's namesake finding himself on the wrong side of history. Before I go further, if you're looking for the simple stats and a rundown of this engine, there are far quicker videos to watch. I am going to get into all the good mechanical stuff, but before that happens, there's going to be an in-depth history of the engine and its origins. You've been warned. The story of the GAA engine begins in the late 1930s. The war in Europe is raging, France is being consumed by the Blitz, and Britain is mustering every last ounce of strength, blood, ingenuity, and hope to stand in the face of what seems to be an unstoppable enemy. The country is producing war material at the fastest pace it can, and the United States, while not entering the war, is working with them to supply equipment and ramp up various industrial sectors of the country to do it. Since the early 1930s, the Rolls-Royce company has been producing a mighty V12 engine famously known as the Merlin. Hand-assembled with surgical care, they are powerful, reliable, and power both the Supermarine Spitfire and the Hawker Hurricane airplanes that are attempting to face down the German Air Force, which is also ravaging the European front, which is rapidly closing in on Paris, France through 1939 and 1940. There was only one major flaw with the Merlin. Britain didn't have near enough of them, nor would they ever with the current rate of manufacture in the country. Enter an engineer named Maurice Oly. The English-born Oly was one of the greatest automotive engineers who's ever lived. From 1912 through the stock market crash of 1929, Oly worked for Rolls-Royce in a number of capacities on both sides of the ocean. Most notably, he worked as the chief engineer at Rolls-Royce's American manufacturing plant in Springfield, Massachusetts. After the market crashed and Rolls-Royce closed up shop in the USA, Oly went to work for General Motors. It was at General Motors that Oly and his team of engineers would develop the foundational principles of automotive suspensions that are still the bedrock of the cars we drive today. He introduced skid pad testing, anti-roll bars, the concept of roll center, in-depth analysis of anti-dive and anti-squat principles, the detailed analysis of lateral weight transfer, and he even worked with companies like Goodyear on tire development. Now, this guy was a genius. What the heck did he have to do with a Ford tank engine? In 1939, with their backs feeling ever more squeezed against the wall, Rolls-Royce turned to an old friend. They contacted GM and asked if they could have Oly back on a leave of absence for the duration of the war to help their effort. Oly was assumed to be the perfect guy to work on Rolls-Royce's behalf in the USA to secure manufacturers for parts and subassemblies, maybe even whole engines in America. During World War I, he had done virtually the same thing for the company, aiding it with contractors to assist with parts and components for their engine that they made at that point called the Eagle. The following timeline and information come from Maurice Oly's book, which is called Chassis Design, Principles, and Analysis. Now, there is a section in the book where he talks about the lead-up to World War II and the things he was involved in. These things not only surround the Merlin, but actually surround the creation of the GAA tank engine as well. In August 1939, while in Detroit working for General Motors, Oly receives a cable from Rolls-Royce imploring him for help. He asks his bosses for and receives the ability to take a leave of absence to aid Rolls-Royce in their war effort. From that point until June of 1940, he is spending all of his time working with potential suppliers for Rolls-Royce. This includes setting up deals for machine tools and dies, an unsuccessful run at Packard to make some small sub-assemblies for the Merlin, and getting a contract with Wyman Gordon to become a crankshaft supplier for the company. Not only did he negotiate the contract for the crankshafts, he then went to Republic Steel to get a contract for the specific alloy they needed for the cranks to meet the company's spec. He then managed to land the Bauer Roller Bearing Company as a supplier for Rolls-Royce engines as well. It's in June of 1940 that the GAA story forms up under an internationally awkward circumstance. This is when Rolls-Royce attempts to send Oly a complete set of blueprints for the Merlin engine so he can use them for his manufacturing mission. According to Oly, these documents are intercepted by the U.S. Treasury Department, transferred to the U.S. Air Force, and were kept under guard at Wright Field in Ohio. He waits for an entire week until he's informed that the Merlin blueprints can be picked up. During this same week, William Knudsen, who FDR named the Commissioner for Industrial Production in the Office of Production Management, approached Ford about building the necessary engines under license from Rolls-Royce. Ford Motor Company responded favorably to this idea, So, with prints in hand, Oly hot-footed it back to Detroit and over to Ford. Oly then went the extra mile and had some Merlin components rush shipped from England to Detroit so the engineers could get their hands on them and see what they'd be making. Upon his arrival, Ford engineers pounced on the prints, and according to Oly's account, they were duplicated, photographed, and retraced with a speed he could hardly believe. Within weeks, parts were starting to be produced, including the massive crankshafts. Word had leaked to the media that Ford would be building these engines, and it seemed the deal was in hand. But it wasn't. Despite the fact that Ford had accessed every possible piece of existing data and had analyzed physical engine parts, no formal contract had been signed. Worse yet, Henry Ford's knack for being on the wrong side of seemingly every major issue of the mid-20th century was about to cause a massive problem. Henry Ford refused to sign the contract. Knudsen got word and flew to Detroit. He was embarrassed and he was incensed. And when he got there, he was effectively thrown out of Henry Ford's office. The problem? Henry Ford had stated previously that he would have no qualms about manufacturing anything for American defense and the country's armed forces, but he was completely unwilling to entertain the thought of building anything that would be used by foreign powers, even our allies. When he got wind of the fact that the majority of the engines that they would be producing would go back to Britain, Henry Ford refused to comply. Remember Packard? Previously, they had refused to build small subassemblies for the engines, but they were then contacted by Knudsen and his department and asked if they would be willing to build the entire engine program, and they readily agreed. Oly immediately transferred the project there, and its success was unqualified through the war. Oly did see something very curious, though, as he was headed out the door at Ford. As he reports in his book, quote, "An engine design appears and is built in extremely short time and on a dynamometer. It is dimensionally the Merlin, but without a single Merlin detail. With fuel injection, cast crank, aluminum block with dry sleeves, etc." End quote. Maurice Oly got a sneak peek at the first test mule of what would become the GAA, and while clearly frustrated, he was awed in the fact that Ford was able to take the Merlin design, alter it, and create a running prototype in as much time as it might have taken Rolls-Royce to prototype a handful of individual components back in England. So now we have to switch gears. Remember, at this point, we're still talking about aircraft engines, big V12 ones. The kind that Henry Ford shrewdly knew there would be a major market for in the coming years, and the kind he assumed he'd be able to flood the U.S. military aircraft market with, so long as he was able to outdo the competition. At the time, domestically, that competition was another large V12, the famed Allison V1710. But once again in this story, Henry Ford misplayed his hand. We now turn to a crusty, near 80-year-old document entitled Record of Army Ordnance and Development in World War II. History of Development of Ford Tank Engines. The report begins by talking about how the Ford Motor Company recognized a market need for aircraft engines, so they would embark on building their own. Remember, the Merlin was a 60-degree V12, displacing 1,650 cubic inches. The report states, quote, "An upright, 60-degree V12 liquid-cooled engine with a displacement of 1,650 cubic inches. This was selected because of past experience with Liberty and Rolls-Royce engines. It was paramount that the end be achieved from a high-output viewpoint, both in horsepower and quantity of production. Design studies began in July of 1940. End quote. By mid-August, Ford's brilliant plan to take over the domestic military airplane engine market had been shot out of the sky. Despite the fact that their prototype V12 was already making 1,800 horsepower without breaking a sweat, Knudsen and everybody else had bad news. The Allison V12 engine had been developed and implemented in volume years before Ford got the itch to make an airplane engine. The Army Air Force had millions invested in parts and spares, the training of mechanics and service people, and more. They didn't want another V12 engine, no matter how whiz-bang or strong it was. But they did need a tank engine. The M4 Sherman was now having a production boom of its own, and that was causing its own problems, specifically when it came to power plants. Up to this point, most of them were powered by an R975 Continental air-cooled radial engine. There were others powered by a pair of Detroit 671 diesels meshed together at the flywheels, and yet a smaller number was powered by the incredible Chrysler 30-cylinder multi-bank engine that was a collection of 5 inline-6 power plants mounted in a pinwheel configuration. Despite these options, none of which were fantastic, the Army needed more, and this big Ford engine with some changes could fit the bill. And boy, did it ever. Hurriedly surveying the existing medium-duty tank engine compartment, Ford engineers suggested that by cutting the length, and that is using 8 of the 12 cylinders of the already designed and partially developed aircraft engine, it would be possible to produce within a reasonably short length of time an engine that would meet the necessary power plant requirements and that would fit in the existing hull with a few slight alterations. The report then lists a lengthy number of requirements, such as the need to be able to survive at least 600 hours without an overhaul, to have the power to pull up to 60% of the tank's weight, allow for proper cooling in extreme conditions, and operate in a wide power band as to minimize gear changes made by the driver. Tongue-in-cheek, the report continues, quote, "In the absence of this valuable knowledge, which Ford Company ultimately acquired the hard way, they proceeded on September 15, 1941 with the design layouts and details of a proposed engine that, as manufactured, assembled, and placed on a test stand by January 14, 1942, within a period of 5 months. At this point, the GAA was officially born, and while its birth was certainly one of the more bizarre processes in Ford's history, the end result was one of the most incredible engines of its age. And for my money, the GAA is one of the greatest V8s in the history of internal combustion engines. Ford did not copy the Merlin. There were some similarities in layout, but mechanically the engines were vastly different, and we're going to get into all that stuff in a minute. But what made the GAA so incredible for the 1940s and even today? Let's start explaining that from the bottom. The engine used a cast aluminum block with dry steel liners, and it had aluminum cylinder heads with hemispherical-style combustion chambers, a centrally mounted spark plug, dual overhead camshafts, and 4 valves per cylinder. The intake valves measured 2.12 inches, and the exhaust valves measured 1.9 inches, or 54 and 48 millimeters respectively, and remember, there was 2 of each. The exhaust manifolds were not massive cast iron lumps, but rather made of stainless steel halves that were welded together to make the finished pieces. This was a big weight savings. At 1,100 cubic inches, or 18 liters, it's the largest production V8 engine of all time. The bore was 5.4 inches, or 137 millimeters. The stroke was 6 inches, or 152 millimeters. The compression ratio was 7.5 to 1, and the entire engine weighed 1,470 pounds. The alloy construction was from its original intention of aircraft use, where weight was always a concern. The rated horsepower of the engine was 500 at 2,600 RPM, and peak torque was 1,100 foot-pounds. It made more than 1,000 foot-pounds from just over idle all the way through its rev range. Reports state that the engine could be revved to nearly 3,800 RPM before valve float began. If you're scratching your head as to why the V8 made 500 horsepower, whereas the V12 was making 1,800 horsepower in the dyno, the reason is simple: boost. The big V12 was supercharged. In the case of this engine, naturally aspirated. Induction was by carburetors, either the Bendix-Stromberg NA-Y5G on the GAA version, or the Bendix-Stromberg HD5 or HH5 on the GAN version. The GAN version had a lower vertical profile as to fit in different pieces of equipment. Inside this engine, there was a flat plane 180-degree nitrided cast crankshaft. The connecting rods were forged I-beam style units that were shot peened after being forged and machined. The engine used cast aluminum pistons. Those pistons were of a 5-ring design that had a chrome-plated top ring and used a full floating style wrist pin. Interestingly, there were no chains used to drive anything in this engine. A beautiful and robust series of gears and shafts were used to drive everything from the oil pump to the magnetos and even the camshafts themselves. Another fun fact is that the first version of this engine used an angled corset-style series of main studs to mount the main caps down, creating a lot of clamping force, which was fine for aircraft applications where fore and aft movement of the crankshaft was not at play. The problem was in a tank with a clutch that was roughly engaged more often than not, the crank would walk back and forth in testing, causing main bearing wear. This design was quickly discarded for more traditional 4-bolt main cap, and in time those two were changed to a 2-bolt style main, which were deemed and proven to be strong enough to do the job. Lastly, the additional step of thickening the main webs of the block was taken to avoid any possibility of that fore-aft crankshaft movement. Like all new designs, the GAA had its fair share of teething problems. For instance, the spark plug wires, which were captured in the valve covers, would suffer failures when the temperature in that location reached more than 300 degrees and the wire's insulation failed. An oil cooler was found to be needed to control temperatures. Exhaust valve failures were also a problem with the early engines until said exhaust valves were upgraded to stellite sodium-filled units, and it solved that problem completely. Ford worked hand in hand with the military testers and modified the engines effectively on the fly as these issues were discovered, and really what can only be described as hellacious durability testing by the military. For instance, one of the tests was running one of the engines for 100 hours straight at max load and RPM on an eddy current style dyno. Other testing logs are just as impressive, with engines running through a gauntlet of tests for sometimes nearly 500 hours with no failures as the designs were updated and massaged. It should also be mentioned here that by 1944, the military wanted the V12 engine, effectively the one that started this whole process, and they wanted it put into production for use in even larger and heavier tanks. This engine was known as the GAC. The GAC shared all the same technical specs as the V8, except for the addition of 4 cylinders. So if you've been listening to this the whole time thinking Ford definitely ripped off the Rolls-Royce Merlin, it's time to share some of the reasons why they didn't totally rip off the Merlin, but were certainly inspired by it. If Ford did anything, they kind of Fordized a Merlin, meaning they applied all of their extensive knowledge in mass production, manufacturing, casting technology, and everything else acquired when becoming a singular industrial colossus. Let's start from the bottom with the crank. All Merlin engines used a forged crankshaft, and it was their opinion that it was the only way an engine of this size and power level could be made reliable. Ford had been using nitride-hardened cast cranks for many years at this point and believed in that technology, so they stuck with it, and of course it worked in the GAA. One of the most major differences in the engine came with the connecting rods. The GAA used traditional singular rods mounted side by side on the crank pins. The Merlin used a fork and blade style connecting rod. This made the GAC, the 12-cylinder version of the GAA, longer than the Merlin because the cylinders need to be offset to correspond with the connecting rods. In a fork and blade style rod engine, the cylinders need to be completely parallel. Why was this done for the GAA? In my opinion, simplicity. The fork and blade rod requires more work and time to produce. Back to the whole Fordization of the engine, the GAA was a constant study in simplicity of design and assembly. Next, we go to the engine block. The Merlin block was made of multiple pieces. There was a crankcase, and then there were actual blocks of cylinders themselves that slid down over long studs and were then sandwiched down onto itself when the cylinder heads were installed. Ford's block was a single aluminum casting, and the company was one of the few on the planet that could pull this off in the late 30s and early 40s of something of this size. The monoblock casting technology developed by Charles Sorensen and the creation of the 1932 Ford Flathead V8 was now about a decade or more old. The company had it perfected, and that's why it was one of the few places on the planet that could produce something of this magnitude as a single piece. The Merlin was an overhead cam engine, but it was a single overhead camshaft design that used rocker arms to actuate the 4 valves per cylinder. The GAA was a dual overhead cam engine that removed the rocker arms totally and used cam followers or buckets to actuate the valves. This, again, vastly simplified the valve train and eliminated a bunch of potential failure points with the rocker arms. Roughly 28,000 GAA engines in a couple of variants were produced. Now, in contrast, Packard alone made 55,000 Merlins, and over the course of the entire Merlin engine run, all variants included, more than 168,000 were made. The GAA was, is, and may forever be the largest aluminum V8 engine ever mass-produced. The best part is it was as successful as Ford engineers believed it could be in V8 form, and to a much smaller degree in V12 form as well. While it never powered aircraft, it was the preferred engine of M4 Sherman tank crews and larger equipment during the war. It was easy to service, made arguably the best power, certainly when weight is factored in, and did its job with aplomb across the globe in many different environments. The 1,800 horsepower boosted airplane engine made one heck of a naturally aspirated, grunty power plant for some of the heavier iron the Allies had in World War II. It sacrificed massive horsepower numbers for dogged reliability and simple yet elegant design. If you're interested in seeing and hearing one of these beastly engines run outside of an old tank, I can recommend you go looking around at the tractor pulls. There's not many of them, but tractor pullers do sometimes employ the GAA engine and occasionally in multiples. Why? With boost, these things can produce up to 2,000 horsepower. Now, sometimes that results in massive failure, but a lot of times it results in some glorious noise. You can even find examples of people swapping these things into muscle cars and hot rods for maximum wow factor. That's the story of the Ford GAA, the dual overhead cam war Hemi born of a failed gamble to enter the contentious military aviation industry of World War II. Thanks for watching. Like and subscribe for more automotive, historical, and gearhead content.